bot gives me a message saying that they're going to restart my computer during off hours when I'm not using it, they mean 8:50 p.m. while I'm actively streaming. So they have a very different idea of what these words mean than I do. Boy, that was aggravating. Okay, anyway. The tough part of proving this is to prove that adding that infinite tape on the left side doesn't actually gain you anything. If you haven't looked at it extensively, I personally think the easiest approach to this is actually to think first in terms of multi-tape Turing machines. Um, that's basically Turing machines that have a standard tape that goes infinitely to the right, but it's allowed to have more than one of them. And so you can prove that those are equivalent to a regular Turing machine by doing a bit of reasoning that relies on something like adding a marker somewhere in the center, or not center because it's infinite, but adding a marker somewhere along the way where you can put the tapes onto a single tape. But you can take two tapes and show that you would be able to store them on one tape. And while things get more complicated because you have to do some acrobatics when it comes to figuring out the right place to be at any given time, you can still do it. And so a single tape Turing machine is just as powerful as a multi-tape Turing machine. And the easiest, once you understand that proof, I think the doubly infinite tape becomes a lot easier, because you could think of that as being basically two tapes where one is going to the left and one is going to the right, and they've kind of been glued together, and handle it in exactly the same way as you handle the proof for a multi-tape machine. And the fundamental reasoning is very similar to what people did when they divided up that array for the extensible array problem on exam 3. That, yes, normally we'd want to think of this as one single big array, but actually there's no reason you can't chop it in half and deal with each half separately. In reverse, this same thing works out. I don't know how long you'd want me to dwell on it. I think that should be enough to get you started if you haven't solved this problem yet. Certainly we'll go over it we'll make sure that there is at least one really good answer with detail on Piazza. But feel free to put something in the chat box if you have a sort of specific thing that you would like to have elaborated on regarding that question. 10.6. I think it's not too hard to follow the part where just the what is this question doing part. This is just, your head can normally move one space to the left or one space to the right, whichever one it wants. This is a variant on that machine that says you can still move one space to the right, but if you want to go left, you have to go the whole way left. And probably the most important thing to make sure you understand when you're going to be trying to answer this is that you can put a marker on the tape that doesn't really change what's already there. I think there are some examples that do it, but say you have just zeros and ones on the tape. So you have like 1, 0, 0, 1. If your machine is at this point, like that's where the head is, and you want to be able to find your way back to that later, it's perfectly legitimate to say that I'm going to put a marker at that spot and sort of add to the symbol that's there so that you can find your way back to this later. Without knowing that that kind of thing is allowed, it becomes really difficult to maybe impossible to answer a question like 10.6. And I think for most people it's not intuitive that that kind of thing would be allowed. Um, Likewise, it can depend a little on the wording of the question, but you can usually get away with saying, I'm going to add additional symbols to the tape alphabet of the machine so that I can have a symbol that means something extra for the machine's use alone. Kind of like that hash symbol that I used there. Like you could make that symbol valid for the machine's use, but not valid for its input alphabet, just so that it has a way of denoting that this is only a divider. Or when you have questions where you're marking off the zeros and the ones as used, you're allowed to add something to the tape alphabet. Yes, yes, exactly. Someone pointed out that you can basically just double the size of the input alphabet, and that's basically what you're doing when you add a marker. You're just saying this represents a zero with a marker, but you could call it 2 if you wanted. It's just easier for humans usually to have it still look like a 0, but add some additional mark that says this is a special 0, as opposed to trying to, you know, correspond it to something completely different. And I'll let you tell me what you want to do. I could just give you like a really quick version of how 10.6 works, and that would be kind of a spoiler, or we could wait and talk about it on Piazza. I don't want to dump a whole lot of answers out there if people are just getting started on thinking about the questions and sort of end up short-circuiting your chance to think about it and figure it out for yourselves. So I'll pause for a moment and let me know what you prefer. Okay, no one seems to have a strong opinion, so we'll talk about it on Piazza. And I'm also sure, particularly for these questions that are based off of CIPSR, because CIPSR is very widely used for this type of class, there are probably a lot of solutions out there on the internet. So if you ever find yourself wanting to look for it being explained several different ways, it should be easy to find several different ways that the solution has been written up. You know, probably a professor at Washington University and a professor at Berkeley and a professor at Stanford and a professor at the University of Tennessee have all at some point written their own solutions to using this as a homework problem. And that can actually be immensely useful. Don't cheat yourself of going through the exercise of trying to find an answer. But if one person's explanation makes no sense to you, that doesn't mean you don't understand the problem. It could be that the next person's explanation will make all the light bulbs go off, and suddenly the world will make sense. So I'm going to move on to, yes, we have lots of time. I can move on to problem set 11 a little bit and try to make sure that you're ready to move forward with that. This one has much more difficult to understand questions. So give yourself more time on the understanding the questions part. for example, number 1. Now we have A times B. This is a Cartesian product. So we're defining what this is going to mean. And the brackets tell you it's going to be a set. And this tells you that it's going to be a set of tuples. So what are these tuples made up of? In this case, it's an element from A followed by an element from B for each tuple. So what that translates into is something like, let's say A is 0 and 1, and B is 1, 2, 3. Then your first tuple would be 0, 1. And this would create the Cartesian product contains every possible pairing, where the first element is some member of A, and the second element is some member of B. I realize that reading this kind of math is difficult for a lot of people, so that's why I try to dwell on it and help out with it. The reason that things are stated in math like this rather than just written out in English is that English is less precise than math. So while it's really useful sometimes to have an English explanation of, like, you know, this equation is meant to say such and such, the mathematical demonstration of what it says is the super precise, we are absolutely certain that we are conveying the right idea, and there cannot be any room for misunderstanding version. Having read many hundreds of submissions of attempted solutions of various problems, I can tell you with great certainty that there are a lot of ways that when you're only writing something out in English, you can be unclear when you think that you're being absolutely clear. So that's why we provide all this math. And unfortunately, people find it confusing a bit, and we try to help out with that as much as possible, but we can't get away from it and still be as precise as we need to be. Let's see. Part C is sort of just an expansion on that concept. I know when you first just start reading it, it could seem like part C of number 1 is a completely different thing, but it's actually the same kind of idea extended to get more sets involved. So you'd have set A and set B and set C, and you take one element from each. Or you have set A, B, C, D, and you take one element from each. And it works out to be the same kind of reasoning. But, oops, sorry, I clicked the wrong thing. The same kind of reasoning, but, well, like I said, expanded to more sets. One moment, just double checking to make sure something loaded correctly. Okay, yeah, that's fine. Number 2 here, I believe that is actually a question. I made a couple of videos explaining how to read it last semester. It is incredibly easy to get confused in reading 11.2. We had it as a homework question, and a very large proportion of the class tried to answer the wrong thing entirely because they didn't understand what the question said. But I think I already made videos for that, so I will just try to find them and give you guys the links rather than do it all over again. Okay, number 3, power set of a set. So you're going to want to make sure, before you move on to worrying about what the rest of the question says, you're going to want to make sure that you understand what the power set is. It is like it says, it is the collection of all subsets of A, which means any, like a subset is some grouping of the members from a set that isn't necessarily complete. Like if your set is 1, 2, 3, then your subsets could include 1 or 2 or 3 or 1 and 2 or 1 and 3, etc. But to understand this question, I think it is very worthwhile to make sure that if you're confused by the idea of power set, that you pursue that a little more. Also, I know someone asked on Piazza, I don't remember who, but surjective, um, that's the formal math term. Uh, like there's injective, bijective, and surjective. Um, so you have, for a function, you're going to have a domain, and that's the possible inputs. And then you're going to have a thing called the codomain, and that's like stuff it gets mapped to. So a surjective function is when everything that you could possibly map here comes from something that was over there. Like nothing gets skipped. And I think it is perfectly fair to say that a lot of this, I'm sure to many people, a lot of this feels incredibly abstract. The old ordering of the class had the sort of super abstract stuff first, followed by the more concrete stuff that you guys did first. You guys did the concrete stuff first, and then it goes into becoming abstract. I don't really know if one way or the other is obviously better. But this particular thing that I'm discussing right now is actually stuff that you probably heard about in like high school calculus. There's certainly no reason you would remember it at this point unless you spend a lot of time doing math stuff. But math in some situations concerns itself with whether every possible value is getting used. So when you're, say, mapping from natural numbers to natural numbers, and you're using the function 2 to the n, then you're going to end up skipping some of the natural numbers on the codomain side. Yes, surjective is the same thing as onto. I don't know exactly why both of those terms exist. I think it's something to do with just different sub-schools of math having a disagreement about which term they want to use or something like that. But this, for example, this 2 to the n would not be a surjective function because it doesn't end up that every possible member of this side could be mapped to by some member of this side. So some of them don't get used. And so when it's asking you to show that there is no surjective function, it's asking you to show that there are going to be some members of that codomain that aren't mapped to from any member of the domain, considering the function, the power set function. This problem will probably be very difficult if you don't already understand diagonalization very well. Diagonalization arguments tend to... Oh, thank you. That someone is reminding us that Sipser covers this stuff on page 203. I don't know. I was quiet for a moment because I was stopping to double check page 203 to see that it was actually what I thought it was. But specifically for the concept of one-to-one and onto, I would not be surprised if you could find explanations that you would find much friendlier on the internet from Sipser as well. Um, More friendly than Sipser, I mean, because that's a concept that's covered a lot in high school calculus classes. There are a lot of resources out there that are more focused at explaining it at a very clear and concrete level, because those resources are written for people who are not trying to study abstract math. So when it comes to finding something that explains it in a nice way, that's not too overwhelming or crazy, um, probably actually looking at high school calculus materials would be helpful. And that's not intended as an insult to anybody that you should go back and look at calculus stuff. It's just that when someone like Sipser is explaining things, he comes at it from a different perspective than most people are used to. So hearing it explained from a perspective that's probably closer to how you think on a day-to-day basis is good for getting the right intuition. And then, of course, it's also a good idea to go see how Sipser explains it and to understand the more underlying concrete mathematical rules. I'm hoping that as far as audio stuff goes, maybe when YouTube does the processing later, it'll figure that stuff out. Unfortunately, I'm not broadcasting from campus, so I'm on a household internet connection, and it seems like there might be some hiccups in the bandwidth. And there's nothing I can do at this particular moment to address that, because, I am not the cable company. Let's see, we have 10 minutes. Let's see what we can cover on how the rest of these work. Uh, yeah, make sure that you read this paragraph. It's not actually part of a question, but it's explaining where these questions are trying to go. And understanding this part can help to keep you from going off on a tangent and trying to prove things about these questions that may be impossible or may not make sense or may just end up being a waste of your time. I would make sure that you are familiar with names like this, ETM. That is commonly how the Turing machine with an empty language is named. So I would think probably if it showed up on the final, not the final exam, on exam 4, we would explain it again, but it's helpful to be able to quickly recognize it. And since it's usually always given that particular notation for a name, you might as well just get used to it. And this, just to review it, this is the description of a machine. So this is not actually a set of machines, it is a set of machine descriptions. So M is a Turing machine, that's the description of a Turing machine, and this is limited specifically to machines where the language of the machine would be empty. Oh, this is a good question. Someone is asking, like, why would you need the diagonalization argument? It seems like the power set of a set is much larger than the original set. In another context, I kind of touched on something similar to this on Piazza, but mathematically, the set of like all natural numbers is considered to be the same size as the set of even natural numbers. And that's because you can map one to the other, like in a one-to-one correspondence. Like 1 maps to 2, 2 maps to 4, 3 maps to 6, and this can go on for infinity. So even though it should seem intuitively like the set of natural numbers is twice as big because the even numbers are skipping half of them, when you're actually deciding how big sets are, these two are considered to be the same size. And that's why you have to actually appeal to a formal argument when you're talking about the size of different sets and proving that one can't be put in one-to-one correspondence with the other. Because it may intuitively seem like it's obvious that one thing is bigger than the other, but being intuitively bigger is not the same thing as being mathematically bigger. And this is one of the probably nastiest bits of abstraction in the whole class, that this so completely goes against any kind of intuition that you probably have about how numbers work. Unfortunately, once you're up in the realm of dealing with infinity, numbers behave really weirdly. Does that make some sense for why it would be the case that you have to actually prove this, as opposed to just saying, oh, obviously, once you take the power set, you've got a whole bunch of members from one member, so clearly it's bigger. I'm just pausing for a second to see if anyone wants to ask more questions about that before I dash off into something else. Okay, we only have a few more minutes, so I'm going to move on. But if there are more questions about that later, we could wait, let me double check. Yeah, see, A is not guaranteed to be a finite set, so you can't get out on the, I know exactly how many elements there are, and I can calculate how many elements are in the power set and then show you that this doesn't work. You have to deal with the infinite possibility. Let's see, moving on to 11.5. I believe the clean star operator was actually defined at some length early on in the Udacity videos. So if you skipped over that or you're just not remembering it very clearly, you might want to go back to it and remind yourself of exactly what clean star means and the actual behavior that goes along with this formal notation. I'm pretty sure that this was an exam question a couple years ago. So this is within the realm of what it would be considered to be fair to ask during an exam. Yeah, step one is definitely to make sure that you have a grip on what the clean star is doing. It will be assumed, by the way, that if you were ever to see that star during an exam, you should know what it means, because it was both covered in the Udacity lectures and it popped up in a homework assignment, or problem set rather. So you have definitely seen it more than once, and it's fair game to just assume that you should know what it does. Be very careful for, I would say, all questions related to these topics, that you pay attention to whether it's asking you to show something is recognizable or to show that it's decidable. Because while recognizable is one part of decidable, they're not completely the same thing. And you definitely do not want to start trying to prove that something is decidable if it's only recognizable. And I'll also add that we do not deliberately ask trick questions. So if we ask you to show, you may be able to hear sirens. Unfortunately, there are sirens outside my window. Um, if we ask you to prove that something is decidable, we do not intend to get the answer back that you have a proof that it is not decidable. I have had people in the past attempt to submit answers to exams and homework that said, well, the thing you asked me to prove just isn't true. And if you were to ever legitimately prove that it's not true, like we screwed up on the question and actually it was impossible, you would certainly get credit for that. But we would never do that on purpose. We're not going to ask you to prove something that we know to be false. And we're not going to ask you to disprove something that we know to be true. If we want you to be figuring out the answer, then we're going to be saying, like, either prove it or show a counterexample, or which one do you think it is. But we're never going to say, prove that it's one thing when we know that it's something else. So if you are to, if you encounter a test question where we say prove something's decidable and you're pretty sure it's not, then you should stop and think about what you might be doing wrong, because there's always a tiny chance that we just screwed up, but the odds are that there's something you're misunderstanding and you're about to waste a lot of time if you try to just prove the question wrong. Okay, this verifier question confuses people every time it comes up. Like every semester when this is used, people are confused. The concept of a verifier is actually covered soon. You, in addition to a finite state machine that behaves deterministically, which means it always follows the same path, and you know what step it's in at any given moment. There can also be non-deterministic machines. And when you reach the point where you're discussing the P versus NP problem, which you don't need to understand yet, this is a little bit later, the defining point of what puts a problem in the set NP, I'll just write that so that you can see what that is. What defines a problem as in NP is that you can verify that a solution is correct in polynomial time. So the common example of something like that is factoring. As far as we know, factoring a very large number is extremely difficult and probably takes a lot of time. But if someone were to say, here is a very large number, and here are the things it can be factored into, so they've already given you the solution, then it's very easy to verify that the solution is correct. All you have to do is multiply. And so that entire class of problems is about figuring out what kinds of solutions we can verify quickly. And that's the kind of thing that this verifier is talking about. It's not actually about the NP problems. So you don't need to understand those for this question, but that's where the concept of a verifier is coming from. And people get very confused based on the idea that there's a thing called a verifier that they've never heard of before. But the core idea here is that the verifier is going to take in an answer and some kind of proof that the answer is correct. So, like, pretend we have a, a state machine, and we don't know exactly which states it's going to follow in advance, and it could be very large. I mean, it could be a ridiculously big state machine. And if we wanted to find the answer without knowing it in advance, we might have to search all through this thing and, traverse down every possible tree looking to see if we could find an answer that works. But in this case, we could think of it as having a certificate that shows that an answer is going to work. And maybe that's just a list of ones and zeros that tells you which way to go. So if the first value is 1, then that means we take the right. And if the second value is 0, that means we take the left. And we keep following that path, depending on what the certificate tells us to do. And all we have to do is follow this path and verify that it ends up where it has promised us it was going to end up with that solution that it submitted. And that's essentially what a verifier is doing. So when you're doing this problem, you should note that this says if and only if, which means that your reasoning is going to have to say that if L is recognizable, then the verifier exists. And then you're also going to have to separately prove that if the verifier exists, L is recognizable. That's how you get an if and only if proof. You don't have to have a super deep knowledge of how a verifier behaves to be able to prove this. Honestly, if you get this problem is a good exercise, but if you feel that you're getting incredibly lost on the topic of the verifier, then you might end up spending more time on the question than it's really worth. So don't let yourself just get hung up there indefinitely. You could also skip ahead and watch the future Udacity lectures that talk about verifiers and such. I can remember this question being used in homework the semester I took the class, and then a few weeks later you hit the part where they explain verifiers, and I was like, oh, that's what they were talking about. But yeah, if the verifier itself is throwing you off terribly, you might end up spending more time on the question than it's really worth. So just take that into account when you're deciding how much time you want to spend. But we will certainly make sure that you get a clear explanation of a working solution for this on Piazza as well. Okay, so that's an hour, and I've managed to touch on at least every problem to some degree, every problem in 10 and 11. You can work on those some yourself, and there will be, like I said, we intend to have 2 more sessions of office hours prior to the next exam. So there should be at least one where a discussion will be open, focused on problem set 11, and at least one that'll end up being focused on problem set 12. Hopefully we'll manage to give you something in advance that helps you get started on 12 before you actually go to office hours. I think we'll be able to do that. We'll see. We are really trying on the grading. I would stay longer on office hours, but I actually need to go mess with the grading and try to make sure it gets done so you can get it back. We really, to, Monday night, we thought we were completely done. And then we realized afterward that we had not actually gotten all of the exams. So we've been scrambling to fix it since then. Uh, this this was not even just a matter of anyone procrastinating. It was actually T Squared didn't give us the exams, and we thought we had already graded everything. So for all the TAs who had set aside time to get it all done over the weekend so they could focus on their schoolwork this week, we're having a little trouble getting back to it and getting it all done. But we are working our way through the pile, and that will be done ASAP. I think that's everything as far as logistics are concerned. Oh, registration. My registration is totally separate from you guys now, but my understanding is that everyone in OMS had to join a wait list instead of being allowed to immediately register for a class, and that the spots in the classes were being opened starting, I think, today. So if you're sitting on a wait list, make sure that you are checking your email frequently, like not over the top frequently, but once you're offered a spot in a class off the wait list, the system automatically gives you a 12-hour time limit to either take that spot or lose it. So if you only check your email at 10 a.m. every morning and a spot opens at 4 p.m., then you're not going to find out about it until more than 12 hours later, and the system will have moved on by then, and you will not get that spot. So if you are still waiting for a spot, you're going to want to check in, maybe 10 a.m. and 10 p.m. would be safe, or something similar to that, like when you get up in the morning and when you go to bed at night. But definitely do not ignore your email for days at a time and then think that you're going to get that waitlist spot in the class, because that stuff is totally automated and it will absolutely skip you if you don't respond within the window it expects. So that is my emphatic reminder to pay attention to your registration stuff, because there is a very good chance that you could still get into most classes later and during phase 2 registration and such, but life is immensely less stressful if you get it out of the way now, rather than going all the way into January wondering what class you're going to be taking. So, okay, this is a good reminder. On the registration page, you can go into the student details section, and it'll give you an idea of where you are on the wait list. So you want to be doubly careful to keep an eye on your email if you're kind of near the top of the wait list. But my vague understanding is that they're opening slots in the classes right now depending on how many TAs they've confirmed. So it's entirely possible that they'll confirm 2 TAs for a class at the same time and open up 100 slots. So you don't want to be like, I'm 80 points down on the wait list and I don't need to pay attention to it at all right now. It's possible that they'll end up opening a lot all at once. This is a completely new system for this semester. This approach has never been tried before. So I can't tell you how it'll work out. But it seems like it's meant to smooth things out and like it kind of ought to help. So just do your best to stay on top of your email. So thank you for coming to office hours, everyone, and thank you for being patient with my unintended reboot. That was totally unexpected, and I don't understand why this operating system is designed to reboot whenever the heck it wants, even if I'm actively using the computer. But I don't control it, so I'm stuck. I hope you all have a good night and have a good weekend, and I will see you on Piazza.